so that we at least have a common understanding of what the nuts and bolts are. Some issues may come up along the way. I'm not going to attempt to tell people what to think about the issues, just to, maybe point to some that are there just because they are. The shale extent, both the Marcellus, which is a Devonian shale, okay, the shale extent, both the Devonian, the Marcellus shale, which is the Devonian shale, named after the hamlet of Marcellus, and also the Ordovician shale, known as the Utica shale, named after, guess what? The extent of those runs pretty well up into New York State, and that's one of the reasons that we're having this discussion. Okay? Now, some things that many people I found don't really understand about the whole idea of unconventional versus conventional oil and gas development is this. There's no truly dry gas with no oil residues or nothing like that. And there's no real oil well that doesn't also produce natural gas. It's a spectrum. And so this slide I borrowed shamelessly from the U.S. Geological Survey shows on this corner over here a conventional deposit of petroleum that have broken away from what we consider the source rocks, the shales, because almost all these petroleums started in shales somewhere. And the conventional deposits broke away from them and made their way up through fissures and different things until they hit a capping rock structure, typically another shale. And so what we show in this photograph, in this mock-up cartoon here, is the bottom layer of this mess would be brine. Lying over that would be oil, and over that would be natural gas, because one floats on the other, which floats on the other. Now, a drier well, more like the wells we would be seeing exploited over in our part of the state, would contain mostly brine and natural gas, and maybe a little bit of the wet oils or the wet hydrocarbons coming along with that. Meanwhile, these conventional deposits have been mostly tapped out, and so to get more of the petroleum, what they have to do is they have to go to the source rock, the reservoir rock, the shales. And the problem is the gases and the oils don't really want to come out of there. Okay, developing a conventional well is a little like the project of opening a juice box and sticking in a sippy straw while you're squeezing it. It comes right up at you. Not true of the shale projects, and that's a big part of what makes the projects so difficult. And my slide advancer, oh, there you go. Now, one of the things we have to do in order to exploit shale gases in an economical way is we've got to not run just a vertical shaft down to the shale and then crack up whatever's right around that narrow slice of shale. What we need really to do is we need to go down to the shale and then run horizontally along with the shale and keep our wellbore inside that target formation for a long way. Now, the shale doesn't give up its oil very easily, so wherever you're going to try to get oil and gas from it, you're going to have to crack it up. And they do this by the process known as hydraulic fracturing. So I want to make it clear that I don't use the word fracking or hydraulic fracturing unless I'm actually talking about this step of breaking up the rock. But there are lots and lots of people in this country and across the world who use the word hydrofracking or fracking as emblematic as the entire exploration, production, and transmission process. So long as you know which of those you're talking about, you can talk intelligently about this shale gas industry and the developments. Typically, I'll reserve my use of fracking to the actual step of cracking the rock. But I'm not going to put down people who use it in the broader sense. There's no point to that. Now, the big deal about this, and more than any other aspect of the shale gas developments, is that these horizontally drilled projects use a lot more resources both of human intelligence, of monitoring equipment that's required, and also a lot more concrete, a lot more steel pipe, and an awful lot more water than one of these traditional type shale wells or whatever, more conventional type wells. So if you know of projects that have gone on around here where they drilled down into a sandstone formation, they fractured it up. They were able to probably get away with using about a cubic yard of cement, maybe 8,000 or 9,000 feet of pipe, and about 80 to 100,000 gallons of water with some other chemicals and stuff thrown in, and a bunch of sand. A project like this is a lot bigger, and what I mean by that is we're talking several cubic yards of concrete, thousands and thousands of feet of pipe, and about 5.5 million gallons on average of water, about 50 times more water, about 3 times more pipe, and maybe 3 to 5 times more concrete, depending on your conditions. This, more than anything, is what makes this new kind of drilling different than the old ways, because it's just huge. All right, let's get this thing to work. All right. Now, in order to try to keep a lid on this sort of thing, they try to build wells with lots of layers of concrete and steel. And Chip Northrup is later on going to talk much more about this, and so I won't belabor the issue. What this particular picture, which I borrowed from our former DEC Commissioner Pete Granis, shows is a bunch of layers of steel shown in your red lines, concrete shown in your yellow lines there, and the production pipe coming right down the middle. And this is only of a vertical well. And they show here what we call triple casing. The surface casing with the intermediate casing and the production casing. And the DEC has put out regulations as though this is new. This isn't really new. They've been putting in 3 or 4 casings consistently throughout Ohio, Pennsylvania, and other states around here for years. The problem is even that, radical response to trying to keep, all of the gas inside and all of the other, corruption inside the project area is not always effective, not as effective as everyone would like it to be. And in fact, many of the wells we know have leaked in Dimock and in Clearfield, Pennsylvania, and Hickory and other places like that are quadruple cased, and yet it's not good enough yet. Enough of that. I'll let Chip take the rest away when he speaks with you later. Another facet that is a little new to this industry is the ability, in fact the need, to put more than one well project on a single well pad. And they'll usually not use the same vertical, they'll drill individual verticals, but then they'll run laterals underground out in these pitchfork kinds of patterns, hoping to recover all the gas between these laterals by sending out the fractures in the rock from each of these, so that the fractures from this guy will meet up with the fractures from this guy in the middle and get all the gas that's in between them. That's the strategy. This is called an octopus or a double pitchfork strategy. And the good thing about this strategy is that it limits the number of access roads you have to build into well sites, and also the number of pipelines you have to build out of them to get the product out into market. The bad news of this strategy, or the challenges with this strategy, is if you live next to a project like this, you'll be living next to an intensive phase of construction for years, not weeks, like we're used to with the old traditional methods. Now, on to the chemistry, because after all, I'm a chemist and I have to talk about this, so I'm going to try not to give you a lot of chemical names. What we already have in these shales, these source rocks, when we drill down into them, are of course organic carbon, gas or oil. If we didn't have any gas or oil in these shales, this would be a really boring meeting. We also have some fairly toxic, what we call heavy metals. Metals like arsenic and barium, and in a lot of cases strontium, and some things that you really would rather not have near you. Well, they're already at fairly high concentrations in the shale rock. Typically higher concentrations in the shale, especially the Marcellus shale, than in surrounding sandstones or limestones or dolomites or other kinds of rocks. One of the heavy metals that's found there is also the radioactive element barium. We also have some brine, lots and lots of brine. This area where we see have seen the old development of oil and gas was once an inland sea, the bottom of the sea, because that's where these black shales, these carbon-rich shales form. More of these are actually forming in the deep trenches of our oceans today, and they'll be ready to be exploded in, I don't know, 350 million years or so. Hang on to your hat for that. We also have, especially in the case, like I mentioned, of the Marcellus Shale, radioactive elements. And the Marcellus is famous among geologists for actually being pretty highly radioactive. It's not uniformly highly radioactive. There are hot spots and not so hot spots. Near, not so far from my home, near the upper reaches, the outcrops on the eastern side over by Cherry Valley, I've made measurements of the Marcellus Shale there myself, and they're not very highly radioactive. On the other hand, if you happen to go to the hamlet of Marcellus, that happens to be a hot spot in the shale. And people have serious problems with the radioactivity, especially radon, who live in that area with their basements in the shale. And it's all over the place, but you've got to be careful, and this should be monitored. We also have the possibility of sewer gas, otherwise known as hydrogen sulfide, formed by anaerobic bacteria, which are fairly populous in petroleum-rich areas. This has been shown over and over again. And the point I'm making with that last slide is that before you add anything to the project, just drilling a deep hole, you've got some produced fluids that you're going to need to deal with the hazards from. Okay, we've got loads of salt, we've got some toxic heavy metals, and we also have the possibility of radon and hydrogen sulfide gases all coming up along with the natural gas. And so all of these things require caution, even when you don't add chemicals to the process. The trouble is they have to add chemicals to the process. There's no way out. Water causes shale rock to swell, and the more clay-rich that rock is, and then the Marcellus, again, is a little more clayey than the Utica and some of the other dark shales. The more clay-like it is, the more it tends to swell when it's exposed to pure water. You can't use pure water or your well will swell shut like a self-sealing tire. And that has to be really annoying if you've just sunk a couple of $100,000 into that hole. We also have to prevent bacteria that live in these deep rock structures from doing what they famously do, which is form biofilms, sticky, gooey, black things that plug pores. Because if you want gas to flow from pores in the rock, you can't let bacteria plug them. So here's what you do, you kill them all. And the other thing, of course, is that corrosion is a real threat. As you get deeper and deeper into our Earth's crust, it gets warmer down there. That's what geothermal energy is all about. And at the depths that we're finding lucrative drilling, your temperatures are between 140 and 180 degrees Fahrenheit, just below the boiling temperature. And it's loaded with salt. Well, what do you think is going to happen to your steel drilling parts or any other steel parts down there in a hot environment loaded with salt? Corrosion is a problem on a time frame of hours, not days. So here's what we do. We're going to throw in a bunch of biocides. Not chlorine bleach kinds of biocides. It's too wimpy and weak. And to sterilize 5.5 million gallons of hydraulic fracturing fluid, you need a really breathtakingly toxic biocides. So that's the kind they use. We're going to need some surfactants, some soaps to make our water wetter and to also help control the rock and keep it from swelling and going crazy with the addition of water that didn't used to be there. Flocculants will do the same thing. These help the particles of the rock stick together and not swell in response to water. We're going to need to use a bunch of corrosion inhibitors, the vast majority of which are really very toxic. And also proppants like sand grains or ceramic beads, something, because when you force cracks in the rock, if you just leave them be and let off the pressure, they'll just reseal because there's still a lot of pressure from all the rock that lies over top of them. So we prop them open with grains of sand or ceramic beads or things like that. Those are called proppants. And these days, proppants are more often than not coated with resins so that they stay suspended in your hydraulic fracturing mixture better. And so the plastic resin coating is also of some chemical concern. And then they throw in other chemical conditioners as they need them, but only as they need them because all these chemicals cost money. But if they have a hole with special issues with high scale forming chemicals or a lot of hydrogen sulfide, even so that it's unsafe for the workers there. They've got to deal with that by throwing in some extra control additives. Now, the news about all these chemical additives, more than 200 of these have been approved or tacitly approved in the state of New York for use by drillers. They don't have to tell you what they're all using at one time, because they won't ever use all 200 at one time. They'll try to use just 7 or 8 of these and get away, if at all possible, with fewer than a dozen for any one particular well project. But more than 3/4 of the additives that they have for use, because these tend to not be pure chemicals but mixtures of things, more than 3/4 constitute health hazards, either in the concentrated forms that we have as they're trucked into the well pad, and some of them in very dilute forms, very ridiculously diluted forms that you would have a chance of being exposed to. Say if they have a blowout on a pipe and it leads to a runoff into a stream or a farm pond, and these things have actually been known to happen and cause some of these things right here. We've got some peer-reviewed literature now that details in humans and in animals respiratory diseases, endocrine-type diseases, infertility and birth defects, especially among livestock, kidney, heart, liver, and brain damage. That's recorded mostly in people, and of course, highly suspect occurrence of cancers that weren't occurring before these gas fields, some of these gas fields got going. So this is not just scare tactics. This is what's going on around the world in gas fields that have been in place for a while. The chemicals I call of special concern are these, because it's a short list of chemicals that are especially nasty when they're diluted to ridiculous extremes. So after you've had these people drop off all of this flowback fluid with a publicly owned waste treatment plant, and they don't really know what to do with them, so they just dilute them a whole lot and dump them in the river. And this has been happening some in Pennsylvania anyway. These wind up getting diluted but still released, and they continue to be health hazards in really tiny concentrations, and that's the problem with this, that the bad news bears, except for this one. This one, acrylonitrile, isn't so highly toxic at terribly low concentrations, but because they're using it so much now to coat sand, and there's so much sand going into propping open the cracks, and so much of this acrylonitrile getting loose into streams, that it doesn't matter that it's not that dangerous at tiny concentrations, because we're finding it at pretty high concentrations in streams surrounding gas fields. Sad to say. Other issues that can come up, of course, if you don't take care of these things, is erosion and sedimentation problems. The sedimentation from one well pad and access road has been estimated at 8 tons per year. That's for every individual lateral that's run off that gas well pad. And in the state of New York, they do a pretty good job of getting people to control erosion and sedimentation on the well pads and the access road. But then when trucks get out onto the town roads and the county roads, there are no more straw bales, there's no more control. And as they get pounded into a powder, then the erosion and sedimentation picks up a pace. And you don't actually have to wash nasty chemicals into a stream to kill everything in it. If you're just washing in silt, it's just bad. And so that's one of the big hazards that I think it's an unsung story here. The fragmentation, I just let the picture be worth 1,000 words. This is 40-acre spacing of typically oil wells in the northwestern Pennsylvania in the Allegheny National Forest. This photograph was taken from the air in December of 2009. And the biological issues are that it's typical now to do the top hole drilling. Well, the very top hole, like the first 1,000 feet, these days is usually actually drilled by a water well driller locally. That's the good news, because our local water well drillers have to be licensed in the state of New York, unlike gas well drillers who don't have to be licensed at all. But typically with the top hole drilling, they're going to try to drill that with compressed air, or at most air and a foaming agent, and not using any biocides, because biofilms aren't generally a problem until you get down below 1,000 feet. What this is achieved in some instances, and now tophole drilling on air alone is prohibited in Colorado and Wyoming for this reason. They've actually pulled up some of the microbes from the deeper rock structures, brought them up into the drinking water aquifers before they can case and seal the well, and contaminated aquifers not with chemicals, but with bacteria, which typically form sewer gas. And so people who didn't before then have problems with a rotten egg smell in their water suddenly come up with it, which is just annoying. In some cases dangerous, but mostly just annoying. This is the bacteria that does that, one of the bacteria that does that. And if you can say desulfovibrio desulfuricans 5 times fast, well, I don't have any money, but I'll find out another word I can give you. All right, we're almost there. You've heard about the story with the trucks, and it's approximately true wherever we've seen gas drilling taking off, especially in now the advanced wave of development. Typically after well sites have been being developed and they know where the hot spots are for good drilling as opposed to dry hole drilling, you're going to see a lot of trucks in, at least 1,000 trucks per truck trips per well lateral. Once a gas field has been in place for about 3 years, they tend to do more recycling of water and more piping of water where it needs to go. But while they're in the exploratory phase, there's not much of that recycling and piping that can happen because they don't know where they're going with it yet.
5 minutes, Ron.
Thanks. I won't need it all. Road spreading. Sometimes road spreading is approved by local towns and counties. That doesn't happen a whole lot around here. And sometimes, as is the case with this particular truck in Wetzel County, West Virginia, it was actually not approved, it's just happening. And that's because this is a cheap way to dispose of water that's otherwise expensive to dispose of because nobody seems to be able to treat the stuff. If you don't have enough boots on the ground or people like this alert person, with a camera to try to document this and get on top of it, you will see this because it simply has been a corollary of doing business as usual in all the gas fields we know of. Pit problems. There's been a big to-do made about the fact that New York State is no longer going to allow the use of pits in drilling operations for oil and gas in New York State. That's actually not exactly true, not even by the guidelines that have been put out so far. They're going to eliminate the use of pits for the large-scale projects only. So traditional type wells, the vertical wells, infill wells that they might drill on a otherwise multi-well pad, that's a traditional size and scope of well, they'll continue to be able to use pits. And this particular pit came from far, far away in Preston, New York, just west of Norwich. And the difficulty that we have here, now this is a small pit because this is just used for drill cuttings and drilling muds. And the problems that we have here is that it's already not meeting regulation in a couple of important respects. It's supposed to keep a minimum of 1.5 feet of freeboard or headspace at the top of this pit in New York. That's been the law for quite a while. And one of the issues we have in New York is there aren't enough inspectors to really enforce. And so a lot of things on the books get ignored. I'll talk about a little more of that in a second. And so this pit has overflowed. It must have rained there. Maybe it rains here too. I won't belabor this slide. I'm a construction professional, and Murphy's Law sometimes takes over, and everybody who's worked in construction knows that that's how it goes. And then when things go wrong, they circle the wagons, and like any other project like that, the finger pointing starts and the truth telling stops cold. It's just what it is, and it's not this industry alone, it's every construction thing I've ever been involved with that had something go wrong. Thanks. Orphaned and abandoned wells are a big deal because we have a lot of them. The further west in the state you go, the more we have. And what's the trouble to me is that historically, only about 14 of these have ever gotten plugged that we know of. But the recent record is less than half of that. So the DEC is actually losing control over this area of regulation. Sorry, I have to tell you that. So finally, I'm going to close with my contact information slide. This is where you can get in touch with me to to ask questions. I am a member of Sustainable Otsego, although I'm busy enough, I don't see much of those guys these days. Again, I teach chemistry and biochemistry at SUNY Oneonta. This is my personal email address, rebishop@hotmail.com. Thank you very much.